So today we are going to discuss the powder crystal method. In the previous lecture we have discussed the Laws method and rotating crystal method. So from Laws method of X-ray diffraction we obtain the crystal symmetry. That is if crystal is four-fold symmetry, have four-fold symmetry, that Laws pattern will also have four-fold symmetry. So but it cannot determine the crystal structure. So therefore to overcome this difficulty we use the rotating crystal method. So in this fix the wavelength of X-ray, incident X-ray, and we vary the is a angle. We vary the angle, and therefore from here we can calculate the your crystal structure by obtaining the that is primitives, that is ABC along the that crystallographic axis. So therefore from there we can resolve the crystal structure. But in these both methods we require the precise mounting of a crystal on certain axis means a, b, and c axis. So it is very a difficult task, so because we are using a single crystal. So therefore to overcome this difficulty we we use the that is crystal in powder form. So in the powder form we have many crystallites. So in 1 millimeter cube sample we have 10 to the raised to power 12 crystallites. In this 1 millimeter cube, this in this sample we have 10 raised to power 12 crystallite means when we create this single crystal in powder form, there are so many small crystals in the powder form, so they are oriented in different directions. So therefore all possible diffraction planes are available for this crystal method. But the diffraction underlying the underlying law for this diffraction, this method, is also Bragg's law, that is 2 sine theta and lambda. So which means when the values d and this theta matches this condition we obtain a diffraction pattern. So means the main law is this law, this is Bragg's condition. If this condition is not satisfied, there will be no diffraction pattern in X-ray diffraction. So this method was independently developed by Dewey, Scarer and Hull. That is Dewey, Scarer and Hull. So in this method, so this is X-ray source. So this is filter. So there are many wavelengths of X-rays are formed here. So what here is filter. It is filter of copper, nickel or molybdenum. So it create a monochromatic X-ray, means its wavelength is fixed. So from here it is collimated by this, using this collimator, means we are creating the parallel waves of your X-ray. This is collimator and this is your photofilm. So on this photofilm we obtained that means we obtained a diffraction pattern which obtained this, which obeys this Bragg's condition. So means the values of d and theta which matches this condition will form this diffraction pattern. So since this is your specimen, there are I have told you that there are large number of crystallites which are oriented in different direction. Therefore there are so many Bragg's planes are here. So there will be so many diffraction pattern for different Bragg planes. So this is your photofilm. So this photofilm is being viewed from this upper side. This means this is the overview of this device color camera. So this is photofilm, this is very small. So since I have told you there are so many crystallites here, so there means there are so many black planes, and diffraction pattern will be composed of very large planes. So these diffraction pattern will be obtained on the this will be lie on the surface of this surface of a cone. So means this is your sample, powder sample, which is placed in a capillary tube. This capillary tube is made up of it's a non-diffracting surface, means this will not diffract, means this capillary tube will not diffract your X-ray. The X-ray will be diffracted by the this crystallites. So this means what I have told you, this will form a cone. This will be a surface of cone. This will form a cone like this. This will be from, suppose this X-ray will enter from here and exit from here. So this is forming as a cone. Because this X-ray photo film is very small, so this cone will touch this X-ray here. This part is here and this part is here. So if this X-ray is back reflected, therefore there will be cone for, there will be a cone for, that means for back. So this will be the back reflection cone, but I'm suppose I'm using this cone. So I have told you that this film is photographic film is very small, therefore this diffraction cone will only intersect this photo film on this and on this for this particular solid angle. Since we know that what is solid angle is 4 omega radians, so this suppose this is 4 theta radians. So this, so it is so since this is very important because this angle is in radian, so further I have to convert this into degree. This will be 4 theta. So this will be cut on this. There can be many cones depending upon the orientation of that particular back plane, because there are so many orientation, so many crystallized, there will be so many orientations. So there will be, this is for particular d and particular theta. So there will be so many values of d and theta which are satisfying this condition, this back condition. This is for particular theta and that is d. So therefore suppose this is, since this is circular, suppose this your photographic film is flattened on flat surface, so this will be formed like this. This will be so these so since the cone is large, therefore it will cut this one from one side on the photograph film, and this will cut on the photograph another side of photographic film. So since because I have told you the film is very small, so when this film is dwelt and this is laid flat on the surface, so this will be the pattern. So this distance will be s1, this will be for particular back plane, s2, this will be for another angle theta 3, this is for theta 2, this is for theta 1. So this is the your distance between the two sides of cone. This is for another angle, this is for another angle. So since if s1, s2 and s3 is the distance between the symmetrical line obtained on the photographic film which is laid flat, and if r is the radius of the photographic film, so if s1, s2 and s3 are, that is distance between symmetrical film, between symmetrical line obtained on the film which is laid flat, and are we the radius of that cylindrical film. So 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 therefore what will be the your what will be the theta? Since we have calculated this is as a solid angle, so how to calculate the angle? So angle, so we know that angle is that is 4 theta 1. Suppose 4 theta 1, the angle is arc upon radius. So arc is like this, so this is s1 and radius is r. This is in radians. So if you want to calculate this into degree, so in degree, so because what is the relation between radian degree? Relation is radian will be 180 upon pi into degree. So therefore in degrees this will be 41 s1 upon r, this will be multiplied 180 upon pi. So this will be like this, that which इसको मैं सब लिख सकता हूँ 4 theta 1 upon that is 180 degree into s1 upon pi r. So this will be theta 1 upon 45 s1 upon pi r. So therefore theta 1 will be, that means 45 degree into s1 to pi r. This in case of radius. So if you write this in case of diameter, this will be theta 1, that will this will be d by 2 will be upside, this will be 90 degree s1 pi into d. So since radius is diameter, half of the diameter, this is for particular angle, solid angle in degrees, this is in degrees. For s2, in case of s2, this will be theta 2 will be 90 degree s2 upon pi d. For theta 3, this will be 90 degree s3 upon pi d, and so on. So from here we can calculate the angle. So by using this into your Bragg's law, we have calculated the angle. We can calculate, we have the value of lambda, so we can calculate the d. So we can calculate the interspacing, interplanar spacing. So by using by calculating the interplanar spacing, we can calculate your crystal structure. So in case you want to understand this, so you can understand from using this diagram. So since this is diffraction cone, so here this is so this will be the solid angle 4 theta 1. So here s1 is, because this is cutting your photographic film, this will be, this line will be this, and this will be this, cutting this line. So this will be s1, and this will be the radius. You can calculate, this is the radius, so the angle will be this distance, your arc upon radius, this will be the r. So you can understand from this from this diagram. Since we have calculated these angles theta 1, theta 2 and theta 3, so now by using these angles theta 1, theta 2 and theta 3 in the Bragg's condition, the distance between the planes of the crystal can be calculated. So now by using the distance between the planes, you can say that interplanar distance can be calculated. So by using that interplanar distance, we can interpret your crystal structure. So you can say that we can resolve the crystal structure. So let us give me for example, so if we know that what is the your Bragg's, your condition 2D sine theta, this is n lambda, so this is your Bragg's condition. So now how we can use so I'm showing that how can we can use. So since for cubic crystal your D is A, because from here A, B, C are equal, B cubic crystal A equal to B is equal to C. So this will interspacing plane spacing is calculated by this formula for this cubic crystal. So put this D into this formula, this Bragg's condition. This will be A S square plus K square plus L square into sine theta and lambda. So we can put the value of theta 1, theta 2 and theta 3 here. N is the order of reflection, which can be 1, 2, 3, and lambda is fixed here in this powder method. So squaring this equation we will get, this will be A square divided by S square plus L square, and root will be gone, here will be under root, and root will be gone by taking square. This will be sine square theta n square lambda square. So sine square theta will be n square n, we can say n lambda upon 2a का whole square into s square plus k square plus l square. So this will be sine square theta will be, you can say, directly proportional to s square plus k square plus l square. Why this is proportional? Because this will be constant, n is constant for particular order of reflection, lambda is also constant, a is the lattice parameter, it will be also be constant. So you can say that this sine square theta is directly proportional to this Miller indices, square of this Miller indices. So this is how you can calculate your interplanar spacing by using this formula. Theta is here, we can calculate this h, k and l by placing your crystal along that particular axis. So this is how you can calculate.